So a few years ago, I had a student that learned that I was big into cycling and invited me to come out to his place, Hellybuck's Cyclery. And I said, "Where's that?" He goes, "Oh, it's on the 67,000 block of Mound Road." I just looked at him. I said, "Well, there's no way I'm going out to 31 Mile on Mound. I live here in Royal Oak." He looked back. He said, "Well, how'd you know that?" I'm like, "Well, it's pretty easy. There's a nice little functional relationship between the mile roads and street addresses. So I'll share that little functional relationship with you. If you take a mile road times 2,000 and add 5,000, that gives you your address. Now, this is on the major north-south roads. It's not going to hold true on certain city streets. It only holds true to, a certain distance south. But it does work on like Telegraph, DeQuinder, Mound, Ryan, Southfield, Woodward, etc. So, for instance, at the corner of 11 Mile and Woodward here, there's a Jack's Car Wash and gas station. And the address there, well, if you're the post office, you're going to take 2,000 times 11 plus 5,000 gives you 27,000. Great. But how did I do my magic? I mean, he didn't give me the mile road. He gave me the address. I had to go backwards. So the idea of going backwards is what we're going to talk about. It's an inverse function. Now, functions start out, the things you put in the function, those are your x values. So that's your domain. The things that you get out of the function, that's your range. That's the y values. So a function goes from the domain to the range. The inverse function goes the other way. It's going to take you backwards. So what our goal is in studying this is to figure out, well, how am I going to go backwards? What's going to take me from the address and tell me the mile road? Now, this isn't as quite as a cool trick as it used to be, because everyone's got GPS on their phones and Apple Maps, Google Maps, that kind of stuff. So it's not as cool as it used to be, but it's still kind of helpful. So let's play around with this and see what we can do. Now, what I'm going to do to get you into this a little bit is we're going to throw away the thousands from this. We're just going to understand that, okay, this is in the thousands. And let's start at 1 mile road. Now, I think 0 mile road would be Ford Road. So 1 mile north of that is Warren. So f of 1 would be what? 7. So 1 mile road would put you in the 7,000 block of a major north-south road like Telegraph. How about move up to 3? All right, 11. 3 times 2 is 6, plus 5 is 11, and one more at 5. 15. Good. Now let's plot these points. Let's plot them. I've got a nice XY axis here. So you're going to have to kind of estimate them a little bit. We've got 1 and 7, which is about here. And then 3 and 11, which is about here. And then 5 and 15, which is about here. I've got some rulers up here if you'd like to borrow one. Help yourself. But we're going to get a nice graph of our function. I don't know. I regret grabbing the ruler because it shows that I didn't exactly draw a straight line. That's okay. We get something like that. So that's our function. Call it f. Y equals f of x. But the f of x is not what I'm interested in. I want a different kind of function. I want a function so that if I say, oh, I'm in the 7,000 block of DeQuinder, then it tells me what mile road I'm at. In fact, for this new function, if I put in a 7, what do you think I want to get out of here? What do you think I should get as an output? A 1. If I put in 11, what should I get out? And 15 and 5. Good. So let's plot these points. So 7 and 1, about here. Then 11 and 3, about here. And finally 15, and 5, about here. So let's graph those. So this is the graph of my inverse function. Now, let me give you some notation for that. Well, no, let's not. Let's just, yeah, let's do it. It's called f negative 1 of x. That's your inverse function. Now, we don't actually have an expression for that yet, but that's our goal. Our goal is to find that expression. Now, one of the things that I'd like you to notice is that when we went from the function to the inverse, we kind of reflected its graph around this line. Let's see if we can't figure out what the equation of this line is. And, you know, along the way, maybe we'll do a little bit of review here. So, the general equation of a line is y equals mx plus b. What's b represent as part of that? The y-intercept. So what's the y-intercept? So the y-intercept is 0, so, okay. All right, so this becomes y equals just mx. Now the other part is the slope. That's the m part. And let's think of the slope this way. The slope is the rise over the run. So let me pick 0, 0 as a starting point, and maybe another point up here at 9 and 9. So if I wanted to calculate the slope as being the rise over the run, and going from this point to this point, how much of a rise did I experience? 9. And the run was also 9. So really, m is a 1, b is a 0. So I get the line y equals x. These two graphs are symmetric around the line y equals x. One is a mirror image of the other around that line. And that's something that I want you to know about these graphs. Actually, there's 3 conclusions that I want you to have, and I left a blank here so that we can write that. The graph of f of x and the graph of f negative 1 of x. Now that negative 1 is between f and the parentheses. Are mirror images around the line y equals x. So one is a mirror image of the other. Let's pause for a second and practice that before we move on and figure out how to actually calculate the expression for g. So on the back, I've got 8 graphs. Okay, sorry. So the graph of f and the graph of f inverse are mirror images around the line y equals x. Sure. So on the back here, there's 8 different graphs. There's 4 functions and their inverses. And so what I'd like us to do is try and figure out what are the function and inverse pairs. So for instance, if I take this graph here, and by the way, what would you guess this is the graph of? Yeah, y equals x squared. Okay? If I was to take that and try and find its inverse, that means reflecting it, at least in my mind, around the line y equals x. And when I do that, well, it looks like I get c. So as far as my function and inverse pairs are concerned, A goes with C. See if you can't figure out the rest of those. What are the function slash inverse pairs? Should be able to get to the last one by process of elimination. Okay, so which graph goes with B? What's the inverse of B? H, yeah. If we look down here, that graph has been reflected, and you can kind of see that in a different way. Let's take a look at a couple points in particular. Say these couple. So I have a point at 2, 0, another one at negative 2, 0. When I interchange the x and y, like I did on the front side of this handout, I'm going to get points at 0, 2, and negative 2 and 0. So those points interchange, just like the whole graph is being flipped around. X and y are changing places. All right, so B and H. C we've already used, so let's go down to D. What lines up with D? E. And last but not least, the only two remaining pair are F and G. So nice pairings across the line y equals x. So again, that's one of the conclusions that I'd like you to have here. Let's go back now and figure out how we're actually going to find the inverse of this function. And there's really 4 steps. They're down here at the bottom of your handout. So the first step is to replace your function by y. So let me do that up here. F of x equals 2x plus 5. The first step is to replace f of x by y. So y equals 2x plus 5. The second step is really doing what we did with these tables. And with these tables, we interchanged x and y, right? We just swapped their places. So I'm going to do that here. X equals 2y plus 5. And then what? Well, then we need to solve for y. What steps do I need to do to get y by itself? Subtract 5, divide by 2. So that's your first step, second step, third step. Your fourth step is to replace this by f negative 1 of x. That's worth 1 point, but I want you to get that point. So please remember to do that. And that's our inverse function. So our inverse here now has an expression, x minus 5 over 2. Let's check that out and see if it works. So let's see. Let's do 11 minus 5 is 6. 6 divided by 2 is 3. It works. Now let me give you one. Suppose that there's a nice Italian restaurant on the let's see, the 41,000 block of DeQuinder. Where would that be roughly? I'll just use the number 41 and your inverse function. Yeah, be 18 mile, right? 41 minus 5 is 36. 36 divided by 2, 18. So it's cool. Check it out sometime when you're driving around. You'll see that this works. It's kind of a neat little formula there. Okay, how are we looking on this first one? Let's see. Let's practice a couple more, and then maybe I'll give you a different look. You know what? Let's do that now. Let's just give you a different look at inverse functions and see which one you like better. So let me pass out a few more of these handouts. Any questions or comments on what we've got so far? 3. symmetric around the line y equals x. So the angles, yeah, I guess I don't really. I'm not sure exactly what to say about the angles because.
Like, I mean, I know that because our graph, we didn't have exact points to graph on, so they're not.
Right. So if you were curious about the angles, this angle and this angle should be the same. All right. I know it doesn't look like that, and another thing about the angles, and you have to be careful with this. When I drew this graph, I made sure that the scale was the same on both the x and y axes. Otherwise, it gets skewed a little bit and you can't see that. In fact, on this handout, the one that you're getting now, if I tried to do the same thing here by graphing the inverse, it wouldn't look as nice and neat and symmetrical because the scale on the x and y axes are different. Now down here, I corrected that. But up here, if I tried to draw the inverse function, it wouldn't look like the nice mirror image that it is on the previous handout. Yes?
How are these problems going to look like on the test?
On the test, I'm going to ask you, a large part of what you're going to be responsible for is I'll give you a function and ask you for the inverse. So you'll start out here and you'll be trying to work your way down here. We are going to get to some examples on this. Kyle? Say again? Oh, did you not? Oh, okay. Did I miss you guys? I'm sorry. Sure. Okay, so are there any CSI fans out there? Hey, a couple of you? All right, good. So, the original? Actually, my mind candy for a little while was a program called Numbers. Did anyone ever see that? Yeah. Yeah. I would imagine they have it on Netflix. It lasted for about 6 seasons, which was longer than I might have expected, but not as long as I hoped for. It was a cool program. Now, the very first episode started out, and they feature this mathematician who helps out his brother, who's an FBI agent, and he creates a statistical formula to help capture a criminal. Well, what you don't know is that the formula that they showed in the program was actually a real-life formula. It was used by a Canadian policeman to help narrow down the search, and they actually did catch a serial murder rapist using a mathematical formula. So it was pretty cool, and it was actually based in fact. Now, we're not going to use anything nearly so sophisticated. We're just going to look at something that you might look at if you're viewing a scene of an accident and trying to figure out, well, what happened? How fast was the driver going? So there's a formula like this. How fast or how long your skid marks are depends on your speed and the conditions of the pavement. So if it's dry cement, asphalt, that's great. Then you're going to have a high coefficient of friction. If it's ice and snow, this is going to be a lot smaller, so your skid is going to go on quite a bit longer. So you get a nice relationship between the distance and your speed, the distance of your skid mark and the speed. So I put in some numbers here, and for various speeds, you get the associated length of a skid mark. Now, one thing that I want you to keep in mind is that the distance is proportional to the square of your speed. So when I double my speed from 10 to 20, the skid mark does more than just double. It quadruples. Oops, excuse me. Try that again. When I double my speed to go from 10 to 20, the length of the skid mark did more than just double. It quadrupled because it's going up with the square and so on. So this is MPH, and then it's the length of your skid mark. But after the fact, when you're looking at an accident trying to figure out what happened, then, okay, well, what do you got? What information's available to you after it happened? Do you know how fast the car was traveling after it happened? No. But what you do know is the length of the skid mark. So what we want is this new function. We want functions that kind of switch things around a little bit. Instead of starting out with the miles per hour and figuring out how long of a skid mark it's going to be, we're going to start out with the length. And what we need to determine is the MPH. So what numbers would I want here from this new imaginary function? 10, 20, 30, 40, and 50. I want to reverse this. I want to know what undoes this. So I start out with the length and come up with the miles per hour. So on the one hand, you've got a function, and on the other hand, you've got the inverse function. The inverse function takes the output from here and gives you its input. So you're reversing those roles. You're switching them around. Now I've rescaled the graph here down here. You can plot some points and see that you get some mirror image points. And this is again pointing to the same fact that the function and its inverse are mirror images around the line y equals x. So there's the line y equals x. And our goal would be to find that inverse function. I'm trying to remember what value I used for f. Let me just try and take a stab at one real quick. Let's see, so at 10 miles an hour, so I got to figure out what value I use for f here to create this. Sorry about that. So 6 equals. Okay, so I used f was 0.6. So in this example, to create this, I regarded this as being on gravel or dirt and used the high end of this. I used 0.6. So we're going to use d equals s squared divided by 24. That's the formula we're going to use. That's the formula I used to create this data set. So our goal is to figure out, well, if I know what the distance is, how can that tell me what the speed is? So let's kind of rewrite these things. Let me write it in terms of f of x. If I was to write f of x equals x squared over 24, how would I find the inverse? Well, much like we did with our first example, I'm going to replace replace f of x by y, so y equals x squared over 24. And then again, like what we did with our first example, to go from the function to the inverse, you had to switch the roles of x and y. So we'll do that here. X equals y squared over 24. Then we actually have to solve for y. We want to know what y equals in this case. So the first thing that I would do in terms of solving for y would be to multiply both sides by 24 and get 24x equals y squared. Almost done. I'll take the square root on both sides. Square root of 24x equals the square root of y squared. Technically, there's a plus or minus here, but I'm not going to deal with a negative in this formula because we're not really going to be dealing with negative miles per hour. So we'll just take the square root of 24x. And last but not least, replace f of x, or excuse me, replace this by f inverse of x. So replace y by f inverse of x and get the square root of 24x. So that's your inverse function. Again, this function and the original function are going to be symmetric around the line y equals x. And that's a big part of what I want you to know from this. What this is if you put 4 1/6 into this, that's where that would work out. Should work out there. So 4 1/6 times 24 would be 100. Square root of 100 is 10. So that shows you that the first one works. And you can check some of the other ones. Thanks. Okay, so let's do some more practice with finding some of these inverses, because that's ultimately your goal in this section. That and know the relationship between the graph of a function and its inverse. Yeah, please. Rhonda? Which one do you like better, or thought was more useful or interesting? I mean, whatever feedback you want to give me. So, now I did rush through this one a little bit, mostly because I didn't want to repeat everything. But I guess what I'm looking at is trying to decide which one of these, if I was just going to use one, which one would you like me to use? Yes. You can call one, yeah, number one, number two. You can call one skid marks and call one addresses. All right. Yeah, it's yeah, I got a couple little ones myself. I've seen some skid marks, so I regretted that about as soon as I said it. All right. But let's not work on that now. But I would appreciate getting that back from you, say, after break. I'll give you a couple minutes to work on that. But let's work on trying to find some inverse functions. So we'll start with problem number 36. This is section 11.2. So f of x equals 5x minus 1. So the first step is to replace f of x by y. The second step is to do what? All right, replace x with y and y with x. All right, cool. Then what? Solve for y. Good. What should I do to solve for y? All right, add 1 and then divide by 5. And last but not least, please write that with f negative 1. So f inverse equals x plus 1 over 5. That's it. One thing I want to be clear, this notation, and I guess I've gotten used to this notation so it doesn't bother me, but I can certainly understand that a lot of people would think of it as being the reciprocal. Let me just show you that this function has nothing whatever to do with the reciprocal. If I wanted the reciprocal of f of x, I'd have to write it like this: f of x brackets negative 1. And that would be 1 over 5x minus 1. Let's look at these things graphically and see that one of them is the inverse and one of them's not. So on the one hand, we've got just later. All right. So y equals 5x minus 1. Oops. Might help if I... There we go. Y equals 5x minus 1. Let's make that a little darker here. Projector. And this is kind of cool. I can cheat here. And Desmos. I'll show you that in a minute. Let's do y equals, was it x plus 1 over 5? So x plus 1. And if you highlight this, then hit the division key, you can divide by 5. And yeah, does that look about right? Does those look like inverses of each other? We can add in the line y equals x, and they look pretty good. Now let me shut this off, and let's compare it to what would be the reciprocal. Y equals 1 divided by 5x minus 1. So does that look like the reciprocal graph? Yeah, it's a rational function, right? It's a pretty weird looking thing, but clearly it's not the reflection. What's that?
I saw enough of those last night.
Yeah. All right. The cool thing you can do in Desmos, and I mentioned it briefly, is you don't have to have your variable solved for. So I could just type in y equals 5x minus 1, like this, and then say, you know what? To get the inverse, I want to interchange these. So I'll do an x here and a y here, and boom, you got the inverse. So, nice. Okay, let's do some more here. Any thoughts on the first one? We okay with problem 36 there? Why don't you try problem number 40? So in this case, f of x is 2x plus 6 over 3. So go through the motions. I'll give you a hint in solving. One of the things you can do to make your life easier would be to multiply both sides by the LCD. After. 6 over there and divide by 2. Don't forget the notation at the end, F inverse. Everything has to get. Oh, okay. You divided by. Okay, that's fine. So wait a minute. You didn't interchange x and y. You gotta interchange x and y. Okay, you can't cancel these terms. They're stuck together. So just gotta leave it like that. Oh, it's 3. Oh, 3. Oh, that's a 3. Forgot to put my little timeout thing here. It'll remind me next time so that when you guys are viewing this at home, you can just zip forward until I get rid of that thing. So first step, y equals 2x plus 6 over 3. Second step, interchange x and y. So that's going to be x equals 2y plus 6 over 3. Third step, I want to solve for y. So what I can do is multiply both sides by 3, which is our LCD. So 3 here and a 3 here. There's no cancellation here, so I just get 3x equals 2y plus 6. The 3's cancel out here. Subtract 6 from both sides. 3x minus 6 equals 2y. And last but not least, divide both sides by 2. Now, I know it's tempting to want to cancel that 2 into the 6. You can't. Yep, exactly. Those terms are married. They're joined in mathematical matrimony. Don't break up that marriage. You'll be a home wrecker. Good job. All right, so that leaves us with f inverse of x equals 3x minus 6 over 2. Nice. Let's try a couple more. Kind of a peculiar one. Problem number 44. F of x is 1 over x. Seems simple enough. So, walk me through it. Mark? Yeah. Okay, so what they're doing is they're taking both terms in the numerator and dividing it by 2. If you do that, that's fine. That's fine. But what you can't do, what I saw a couple places was people doing, let's see, 3x minus 3. So they just canceled the 2 and got rid of it altogether. So that's what you can't do. Yeah, so one of two possibilities is fine for me. That's fine, and that's fine. Both of them are fine. The only thing that you're going to lose a point on is if you write 3x minus 3, is if you cancel it and get rid of it altogether. Okay? Appreciate the question. Okay, so problem 44. Y equals 1 over x. Kara, what next? All right, so x equals 1 over y. Thank you. Amila, what do we do next? Tell me in general terms. All right. So our next goal is to solve for y. And, you know, a good thing to do would be to get rid of the denominators, as you said. So we can do that by multiplying both sides by y. That gives me yx equals 1. What do we have to do to solve for y here? Amanda? Divide by x. And y equals 1 over x. And that looks like deja vu all over again, right? Isn't that where we started? Where did we go wrong? Why are we getting such a weird result? So if I've done everything right, I get f inverse of x is 1 over x. But that's exactly where I started. Let's see if we can't come up with an explanation for that. So let me get rid of a couple of these graphs. I'll leave that one. Here's the graph of y equals 1 over x. Let me put that back. There you go. Bless you. So, can anyone explain why I got the same thing back when I started? Yeah, it's its own inverse. So you can think of it in a couple ways. You can think of it graphically. If I reflected this graph around the line y equals x, I'm going to get the same thing, right? It's a mirror image around the line y equals x. A different way to think about it is, if you take the inverse of a number, if I take the inverse of 7, what do I get? 1 over 7. If I want to get back, I take the inverse again, right? The inverse of 1 over 7 is 7. So it's its own inverse function. And you're going to see that anytime you have a function that's symmetric with respect to the line y equals x, it's going to be its own inverse. So kind of a strange example there, but one that's worth spending a little time on. Let's try a couple more here. Problem 46. Yeah, please.
When on a task, if we have an answer like that it's its own inverse, what do you want us to write as our answer?
On the test, all I'll be looking for is the inverse. So, right there. Okay? So that's exactly what I'll be looking for. If you skipped all these other steps, I think I'd be unhappy. I want to see some work. Now, chances are you're not going to get something quite like this, but I do want to see some work. I was grading tests for my other class just yesterday, and there's a couple people that had the right answer but didn't show me any work, and they lost some points because I don't think that many people can do this stuff in their heads. So I want to see some work. It's in your best interest, though. If you make a small mistake and I can catch it, all right, you lose a point or two. But if it's wrong, I can't give you partial credit if I don't see any work. So it helps me to help you. All right, which one did I promise? 46? F of x is x cubed minus 4. So a little bit different on this one. We're not stuck with just a linear function anymore. We've got a cubic function. The first step you should have down, it's y equals x cubed minus 4. Second step should be pretty straightforward as well. It's x equals y cubed minus 4, so interchange x and y. What should I do after that? All right. Add 4 to both sides, thank you. X plus 4 equals y cubed. One last step I need to do to solve for y. Very good. Thank you. So take the cube root on both sides. So the cube root of x plus 4 equals the cube root of y cubed. Of course, these operations cancel each other out. I get y equals the cube root of x plus 4. And last but not least, so this is step 3, step 4, f inverse of x equals the cube root of x plus 4. Why don't you try problem number 40? F of x is the cube root of x minus 5. Is it 48? Yep. All right, my bad. 48. All right, now we need to solve. So this is like our work in section 9.7. It's really reflects our work in a couple sections. Um, how are you going to get rid of a cube root? You have to do both sides. Yeah, well, in this step, you're just switching x and y. No matter what, you're just switching. Good question. No, just a direct change of variables. Wherever there's an x, you're rid of y. Wherever there's a y, you're rid of x. Good job. Keep it. Good. So let's work our way down this one. First step, y equals a cube root of x minus 5. Second step, x equals a cube root of y minus 5. Now let me remind you of something that we've kind of seen before, maybe have forgotten. I think a lot of you would probably say, all right, well, I'll cube both sides to get rid of the root. And cubing both sides will work. That's what we will do. But let me help you remember why that's going to work. Can anyone help me write this with rational exponents? Y minus 5 to what power? 1/3. Now, I think it was section 10.4 when we were solving quadratic equations that were quadratic in form that I suggested you raise both sides to the reciprocal power in order to solve. So in this case, what's the reciprocal of 1/3? It's a cube. So if I cube both sides, I get x cubed. 3 times 1 is 1. So I get y minus 5 to the first power. Add 5 to both sides, x cubed plus 5 equals y. And last but not least, f inverse of x equals x cubed plus 5. Yay! All right, you doing pretty good on finding these inverse functions? Yeah, Mitchell? Yeah, absolutely. You can just cube it and skip from here to here. Yeah, I don't need to see that step. I was just kind of reminding you, we actually kind of did the same thing over here. When we took the cube root is effectively raising something to the 1/3 power. So if I raise this to the 1/3 power, the reciprocal of 3, I get the cube root, and the cube root cancel each other out. So it's just kind of a reminder. I mean, we're only a couple weeks away from the end of the semester, so I try and throw in a little bit of review for you of things we've done. Great, so let me give you some homework then. So for homework, oh, got another question? Yeah, sure. One more? Sure. How about problem number 38? F of x is x over 3 minus 1 over 3. So our first step, x over 3 minus 1 over 3. Second step, x equals y over 3 minus 1 over 3. Multiply both sides by 3, right? Let's get rid of the fractions. I mean, it's always a good thing to do. Get rid of the fractions. So I'll get 3x. What's going to happen when I multiply this by 3? You get rid of the denominator. You get y minus 1. And almost done, right? Add 1 to both sides. 3x plus 1 equals y. And last but not least, f inverse of x equals 3x plus 1. Gil? Sure. Yeah, so I actually thought about doing it that way myself. I'm like, that's a common denominator. So if you wanted to bring them together and write it like this, it makes it even easier to multiply by 3, correct? Because if you multiply by 3 here and 3 here, 3x is there. But on the right-hand side, you see you get some nice cancellation. That cancels pretty easily. All right, great questions. Thank you so much. Is there anything else on section 11.2 or comfortable with putting that one in the books? For homework, try 19 through 49, 55, and 61. Those are just the odds in that section 11.2.